Swayam Prabha. Digital India. Educated India.
Welcome to lecture 39 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Estimation of Fixed and Random Effects Model. In the last lecture, we have discussed the one-way error component panel data models. We have considered both fixed effects model as well as random effects model. While estimating the parameters of two-period fixed effects model, we observed that if we directly apply the OLS procedure, because of the correlation between sum of the time invariant covariates and the error component, the OLS estimator is inconsistent. Then we looked at one of the options, say if we take the first difference, then the resulting model leads to consistent OLS estimators for the parameters. Of course, one of the drawback of that procedure is you cannot recover the coefficients of time invariant covariates. Now, in this lecture, we will consider the estimation of fixed effects model when you have more than two observations or more than observations on more than two time periods. We will also discuss the estimation of random effects model. So, first we consider the fixed effects model with more than two time periods. So, we consider the model yit equal to alpha plus xit beta plus mu I plus eta it. Again, we assume that expectation of xit mu I is not equal to 0. Then, as n increases, the number of parameters, that is mu i's, also increases. So, normally in panel data, you have a large number of cross sections, that is n is large. So, it means you have a large number of parameters mu i's. Now, we cannot estimate mu i's consistently, but we can estimate other parameters consistently. Now, we write the model in the form, say y equal to alpha L n t plus x beta plus d mu plus eta. So, we use the vector and matrix notations and then we write the model in this form, where this L n t is n t cross 1 vector with all elements equal to 1. Then this D is I n canonical product L t. So, this is actually a set of n dummy variables, or this is also a selection matrix. You select different components of mu's using this selection matrix. Suppose we regress y on d and then we obtain the OLS residual q d y, where q d is equal to d d transpose d inverse d transpose. Further, we regress x on d, then again we get the OLS residual q d x. Then we run regression between the OLS residuals q d y and q d x. So, basically what we have done? We have pre-multiplied y y q d and we have taken q d x and then we are running regression between q d y and q d x. And then we get the estimator of beta. And the estimator, the resulting estimator is beta hat w is equal to x transpose q d x inverse x transpose q d y. This estimator we have derived in the last lecture also. And this estimator is actually within estimator. We will again come to this estimator when we will discuss the random effects model. This estimator is also called the least squares dummy variable estimator. And when we pre-multiply y by q d, what it does? It leads to the y vector as deviation from individual specific means, but it also deletes the effects which are time invariant, that is, it deletes mu I. So, any transformation that deletes the fixed effect produces a fixed effects estimator. So, we have used this transformation and then we get this estimator. Now, we consider this transformation. Say, suppose we pre-multiply a t cross 1 vector by a t cross t minus 1 matrix. Say, suppose you have any vector y with elements y 1, y 2, y t, and we pre-multiply this vector by matrix F. Then what we get? We get y 2 minus y 1. You have minus 1 here. So, minus 1 into y 1 plus 1 into y 2, and then you have 0 into y 1 minus 1 into y 2 plus 1 into y 3. So, you get y 3 minus y 1 here and you get y 2 here. At last, you get y t minus y t minus 1 here. Now, this produces a t minus 1 cross 1 vector of first differences. So, you get a vector of first differences. If you pre-multiply any vector by f, it gives a vector of first differences. So, if we pre-multiply the model by f, we get rid of fixed effect. Say you have say fixed effect mu I, and then the first difference of mu I is 0, mu I minus mu I 0, and then we can consistently estimate beta by applying OLS. So, means this kind of transformation we have used in the last lecture also, when we were discussing the fixed effect model with 2 time periods. We have taken the first differences and then we have consistently estimated beta by applying the OLS procedure. Now, again suppose you take y bar I dot, means now you are taking the mean of each cross section unit over time. We are taking mean over t. So, y bar I dot is equal to x bar I dot beta plus mu I plus eta bar I dot. Then the model in deviation form is y I t minus y bar I dot equal to x I t minus x bar I dot beta plus eta I t minus eta bar I dot. So, now what we have done? Instead of taking the first differences, now we are taking deviation from individual specific means y I t minus y bar I dot, and then we get rid of this mu I. Now, this model satisfies the orthogonality condition. So, x I t minus x bar I dot are uncorrelated with eta I t minus eta bar I dot. So, you can apply the OLS for obtaining consistent estimators of beta. So, the first differences or differencing from person specific means like this produce consistent and unbiased estimators of beta. In fact, any transformation through which you can get rid of this mu I can work. So, if you take some other transformation and you get rid of this mu I, then that transformation may also work. So, the steps to implement fixed effects estimator are: transform all the variable by subtracting person specific means, and then run OLS on transformed variables. Now, this is what we have done here also in this estimator. When we take this transformation, we pre-multiply by q d, then it produces a vector as deviation from person specific mean, like this, and then you can run OLS on transformed variables. Then the matrix of standard errors of fixed effects estimators is sigma square eta x transpose q d x inverse. We have just used the formula for variance covariance matrix of GLS estimator. So, in linear model y equal to x beta plus u, if u has variance covariance matrix sigma square u omega, then variance covariance matrix of the GLS estimator is x transpose omega inverse x whole inverse, and then you have sigma square u here. Now, here in place of sigma square u, you have sigma square eta, and then q d inverse is equal to q d. So, you get x transpose q d x whole inverse. Then the estimator of sigma square eta is sigma hat square eta equal to u hat w transpose u hat w upon n t minus n minus k, where u hat w is actually the within OLS residual. this is equal to the residual after using this within estimator beta hat W. Testing for fixed effects. Then we are assuming that summation mu I equal to 0, and you want to test the hypothesis that mu 1 equal to mu 2, so on equal to mu n minus 1 equal to 0. And for testing this hypothesis, we apply Chow test. So, what we do? First, we consider the restricted regression sum of squares by using pooled model. We take all the mu i's equal to 0, and then we fit the model, we pool the model for all i's, and then we apply OLS, and then we obtain the restricted regression sum of squares. Restricted in the sense that you are taking all the mu i's equal to 0. Then we consider unrestricted regression sum of squares by using within estimator. So, we obtain regression sum of squares when we are using within estimator. Then your test statistic is f equal to say r r s s minus u r s s divided by n minus 1 upon u r s s divided by n t minus n minus k. And then under H naught, this follows f distribution with n minus 1 and n t minus 1 minus k degrees of freedoms. And now, you can easily form the critical region. You obtain the tabulated value of f, and if this calculated value is greater than the tabulated value, then we reject H naught. Now, we consider random effects model. The random effects model is given by y I t equal to alpha plus x I t beta plus u I t, and then we are taking u I t equal to mu I plus eta I t. Then mu I is uncorrelated with x I t. So, in random effects model, we assume that x I t's are uncorrelated with mu i's. Then we assume that expectation of eta is equal to 0, expectation eta eta transpose is equal to sigma square eta into identity matrix, expectation of mu I is 0, expectation of mu I mu j is 0 for all I not equal to j, expectation of mu I square is sigma square mu, and expectation of mu I eta j t is equal to 0. Then expectation of u I transpose is equal to, actually u I t is equal to mu I plus eta I t, and then expectation of u I t square is equal to expectation of mu I square plus expectation of eta I t square. So, sigma square mu you can say is equal to sigma square mu plus sigma square eta. So, in the diagonal you obtain sigma square mu plus sigma square eta. The variances are these. And then you consider the covariances, means for t not equal to t dash, expectation of u I t dash is equal to you get expectation of u I t is equal to mu I plus eta I t into mu I plus eta I t dash, and this is equal to sigma square mu. So, all the off diagonal elements are sigma square mu. Then you can write it as, in the diagonal you have sigma square eta. So, you can write it as sigma square eta into I t plus sigma square mu into L t transpose. Actually, L t transpose is a T by T matrix with all elements equal to 1. So, you get this matrix. If you take sigma square eta I t plus sigma square mu L t transpose, then you get this matrix, and then we write this equal to capital sigma. Again, L t is T cross 1 vector with all elements equal to 1. Then, if you take expectation of u transpose, now expectation of ui transpose is equal to capital sigma for all I. So, expectation of u transpose is equal to I n chronicle product sigma, and then we write it equal to capital omega. Again, if we make use of this result, say A plus small a transpose inverse is equal to A inverse minus 1 upon 1 plus A transpose A inverse A, then you have capital A inverse A transpose capital A inverse. So, we make use of this result, and then we obtain the inverse of sigma. So, the inverse of capital sigma is equal to sigma square eta I t plus sigma square mu L t transpose whole inverse, and then we make use of the previous result. We get 1 upon sigma square eta I t minus 1 minus theta square upon t L t transpose, where theta is equal to sigma square eta upon sigma square eta plus t times sigma square mu to the power half. And then you can write sigma square eta plus t times sigma square mu equal to t times sigma square b, as we are taking sigma square b equal to 1 upon t sigma square eta plus sigma square mu. So, we get this expression for sigma inverse. Further, if we take sigma to the power minus half, then this is equal to 1 upon sigma eta, then you have I t minus 1 minus theta upon t L t transpose. To verify this result, you just multiply sigma minus half by sigma minus half, and then you can easily verify that you get sigma inverse, this expression. If you multiply this matrix by this matrix, you get this matrix. So, the expression for sigma minus half is this. So, now you know the expression for sigma inverse, and you can apply the GLS procedure for estimating beta. But to obtain the feasible GLS estimator of beta, we need to estimate sigma square eta and sigma square mu. You require these estimators of sigma square mu and sigma square eta. Now, we consider random effects as a combination of within and between estimators. Now, we consider this ith equation, say y I equal to x I beta plus u I. Then 1 upon t L t transpose y I is equal to 1 upon t summation I equal to 1 to t y I t, which is written as y bar I dot. So, this is actually individual specific mean for the ith individual or for the ith cross section. Similarly, you can define x bar I dot. Then we define a n t cross n matrix D of n dummy variables. So, D equal to, you have L t here, then 0 0, then you have 0 L t, so on. In fact, this D is equal to I n Kronecker product L t. And then P d is equal to D D transpose D inverse T transpose. So, as we have verified in the last lecture, P d is also a symmetric idempotent matrix, and the order of P d is n t cross n t. And pre-multiplying the model by P d transforms the data into means, and then the model becomes P d y equal to P d x beta plus you have some error term. Say if you pre-multiply this vector y by P d, then this transforms the data into individual specific means. You get a vector with y 1 dot bar, y 2 dot bar, and so on. Similarly, for x's also. And then when we apply the OLS to this model, we get the estimator beta hat b equal to x transpose P d x inverse x transpose P d y. Again, remember that P d is an idempotent matrix. Now, this estimator is called the between estimator, or this is also called the Wald estimator. So, now you have two different estimators, this between estimator, and then you also have within estimator beta hat w, which is equal to x transpose q d x inverse x transpose q d y. Actually, this estimator is based on the deviation of different observations from individual specific means. So, that is why this estimator is called within estimator, whereas this estimator is based on the individual specific means. So, this is between estimator. The between estimator is constant, but not efficient. Further, if t is large, this estimator is robust to measurement errors, and the reason is it deletes the individual specific effects. So, if there is some measurement error in individual specific effects, then it will not affect your estimator. So, this estimator is robust to measurement errors in x variables. The only condition is provided orthogonality condition mu I uncorrelated with x I t is satisfied for the correct data. So, as long as for the correct data this condition is satisfied, the estimator is robust to measurement errors. Then the information thrown away by the between estimator can be used to construct following within estimator. Say you have Q d equal to I n t minus P d or I n t minus d, d transpose d inverse d transpose. Where Q d is a symmetric idempotent matrix, then we pre-multiply by Q d to entire model. Then actually Q d y is the residual when we run regression between y and dummy variables d. We have already discussed all these steps earlier also when we defined the within estimator, and then Q d x is the residual when we run regression between x and d. So, in fact, we defined the within estimator for the fixed effects model, but now we are considering the random effects model, and then we are defining the within estimator for random effects model, but our steps are the same. We take Q d y, which is the residual when we run regression between y and dummy variables t, Q d x, which are the residuals when we run regression between x and d. So, basically what we are doing, we are pre-multiplying y by Q d and we are pre-multiplying x by Q d, and then we are pre-multiplying u also by Q d. Thus, pre-multiplying by Q d transforms the data into residuals from auxiliary regressions of all the variables on a complete set of individual specific constants. So, this is how pre-multiplying by Q d transforms the data. Then the predicted value from such a regression is the individual specific means. So, you can say the residuals are deviations from personal specific means. Say, what I mean to say is, if you take Q d y, then Q d y is equal to y minus 1 upon t j t y. It is just like the fixed effects model. And then if you consider this part, if you take j t y and you divide it by t, or you can say if you take j t bar y, then you get this vector. Then pre-multiplying by the model by Q d and applying OLS leads to the within estimator this. Again, this is the same estimator which you get for the fixed effects model, beta hat w equal to x transpose Q d x inverse x transpose Q d y. Or you can say the estimator beta hat w is obtained by running OLS on the following equation. Say you take y I t minus y bar I dot, means you are taking the deviation from individual specific mean. Y bar I dot is the mean of ith individual or the ith cross section. So, you are taking deviation from ith individual, or you can say you are getting within differences or within variations. How much y I t is varying from within group mean equal to x I t minus x bar I dot beta. Again, this gives you how much x I t is varying from the individual specific mean, the mean of the ith cross section, plus say u w I t. And when we apply OLS to this model, we get the within estimator, and the reason is because it uses only variation within each cross section unit. Basically, what you are doing? You are running regression which uses the variation within each cross section unit. This estimator is also consistent, but it is not efficient as it uses n unnecessary extra variables. You have used these n unnecessary variables. Then we can write pooled OLS estimator as weighted sum of between and within estimators. So, this is your OLS estimator, and then you can write it as x transpose x inverse x transpose p dy plus x transpose q dy. Remember that p d plus q d is equal to the identity matrix. And then the first part is x transpose x inverse, then beta hat b, the between estimator is x transpose p d x whole inverse x transpose p d y. So, you can write x transpose p d y as x transpose p d x into beta hat b. Similarly, here we get x transpose x inverse, and then you can write x transpose q d y as x transpose q d x beta hat w. OLS estimator is a weighted sum of this between estimator and this within estimator. Then the pooled OLS estimator is constant, but inefficient as it does not incorporate information about heteroscedasticity resulting from repeated observations from same cross section units. Notice that in our model, the errors are heteroscedastic, but here while we define this OLS estimator, we do not take into account that heteroscedasticity. So, actually this OLS estimator is a weighted sum of this between estimator and this within estimator. Then the pooled OLS estimator is constant, but inefficient as it does not incorporate information about heteroscedasticity resulting from repeated observations from same cross section units. Remember that the variance covariance matrix of U is omega, and if you look at the elements of omega, then in the diagonal you get sigma square mu plus sigma square eta. In the off diagonal you get sigma square mu. So, the disturbances are not homoscedastic. Then we consider estimation of sigma square eta, sigma square b and sigma square mu. The estimators of sigma square eta, sigma square b and sigma square mu based on standard ANOVA are, say, sigma hat square eta equal to 1 upon n t minus n k minus n u hat w transpose u hat w. So, what we do? We consider within estimator and then we obtain the residual using within estimator. So, you had W as the residual corresponding to the within estimator. When we fit the model corresponding to the within estimator, we get this residual. And then on the basis of that, we can estimate sigma hat square eta. We divide it by the corresponding degree of freedom, which is n t minus n k minus n. Then for estimating sigma hat square b, we consider this between residual u hat b, which is based on the between estimator. Then we obtain sigma hat square b as 1 upon n minus k u hat b transpose u hat b. And then using the relation between sigma square mu, sigma square b and sigma square eta, we have sigma hat square mu equal to sigma hat square b minus sigma hat square eta upon t. Here u hat w is the residuals from the within regression and u hat b is the residuals from the between regression. So, we can estimate all these variances. Then degrees of freedoms corresponding to u hat w transpose u hat w is, say, in all you have n t observations. Then the ith equation has k explanatory variables. Then corresponding to each cross section you have k explanatory variables. So, n k. So, you take n t minus n k, but for all I equal to 1 to n, summation t equal to 1 to capital T, you had w I t is equal to 0. So, we subtract n from n k. So, you get this degree of freedom. Again, all these estimators are consistent estimators of corresponding variance. In fact, you can obtain the degree of freedom corresponding to this between estimator also. Since you are taking running regression between individual specific means. So, in all you have capital N individual specific means and then you have capital K explanatory variables. So, the degree of freedom is 1 upon n minus k. Then we estimate theta by theta hat equal to sigma hat square eta upon sigma hat square eta plus t sigma hat square mu to the power half. So, this is a consistent estimator of theta. So, these are the steps for estimating the random effect spinal data model. First, we compute the within and between estimators. Then we compute the corresponding residuals and we use these residuals to estimate variance terms. Say you use these residuals to obtain sigma hat square eta and sigma hat square mu, and then using these estimators we obtain theta hat equal to sigma hat square eta upon sigma hat square eta plus t times sigma hat square mu to the power half. So, you get a consistent estimator of theta, and then we run OLS between transformed variables y curl and x curl, where y curl I t is equal to y I t minus y bar I dot plus theta hat y bar I dot, and x I t curl is equal to x I t minus x bar I dot plus theta hat x bar I dot. So, we transform all the variables and then we run regression between y curl and x curl. Now, we consider GLS estimation. Since the disturbances are not homoscedastic, so one cannot use the OLS procedure for estimating the parameters. So, now we go for the GLS procedure. Again we consider the model y equal to alpha ln t plus x beta plus u, and then u is equal to d mu plus eta. And then we consider within model q d y equal to q d x beta plus q d eta, and then your between model is under root t y bar I dot minus y bar dot dot equal to under root t x bar I dot minus x bar dot dot beta plus under root t u bar I dot minus u bar dot dot for all I. Actually, for each I equation is repeated t times. So, we multiply by under root t, or we can also write this model in terms of P d as P d minus j bar n t y equal to P d minus j bar n t x beta plus P d minus j bar n t u. So, we get this between model, means if you multiply y by P d, then what you get? You get all these individual specific means, a vector with all these individual specific means, and if you multiply by j bar n t, then you get deviation from overall mean. So, basically you are getting the deviations of individual specific means from the overall mean. So, this is how you get this model. Again, variance of q d u is equal to sigma square eta q d, because if you take q d u, it becomes q d eta. The term involving mu I vanishes. Further, variance of P d j bar n t u is equal to, say we write sigma square 1 P d minus j bar n t, where sigma square 1 is equal to t times sigma square, and then this is equal to t times sigma square mu plus sigma square eta. Now, we combine 1 and 3, and then you can write these two models as q d y P d minus j bar n t y equal to q d x P d minus j bar n t x beta plus q d u and P d minus j bar n t u. So, we get this model 4 when we combine 1 and 3. The covariance matrix of this model 4 is, say you get the variance covariance matrix of this q d u here, sigma square eta q d, then you have 0 here, 0 here, and then here you have sigma 1 square P d minus j bar n t. So, you get this variance covariance matrix for the disturbances. Now, you can apply GLS procedure. Say you have this model 4, and you know the variance covariance matrix of the disturbance term, which is equal to this. So, you can apply GLS procedure for estimating beta here, and the resulting estimator is beta hat GLS equal to, you get 1 upon sigma square eta x transpose q d x plus 1 upon sigma 1 square x transpose P d minus j bar n t x. You get from here. just apply this formula of GLS. Say if you have this model y equal to x beta plus u, and the variance covariance matrix of u is expectation of u transpose equal to omega, say, then beta hat is equal to x transpose omega inverse x whole inverse x transpose omega inverse y. Now, in place of x we take this matrix, and in place of omega we take this matrix, and then in place of y we take this vector. And then again you notice that this q d or p d minus j bar n t, these are idempotent matrices. So, you can easily verify this expression for the GLS estimator. So, then we write this as, say, w x x plus theta square b x x whole inverse w x y plus theta square b x y, or w 1 beta hat within estimator plus w 2 beta hat between estimator. Here the expression for w x x is x transpose q d x, the expression for w x y is x transpose q d y. Then b x x is equal to x transpose p d minus j bar n t x, and b x y is equal to x transpose p d minus j bar n t y. And then w 1 is equal to w x x plus theta square b x x whole inverse w x x, and w 2 is equal to w x x plus theta square b x x whole inverse theta square b x x. And in fact, you can easily verify that w 2 is equal to I minus w 1. Say if you take w 1 plus w 2, then w 1 plus w 2 is identity matrix. You can easily verify it. So, using these notations, you get this expression for the GLS estimator. So, you can say that your GLS estimator is a weighted average of within estimator and between estimator. This is your within estimator and this is your between estimator. Now, if you take sigma square mu equal to 0, then this implies that theta is equal to 0. And then if theta is equal to 0, then the GLS estimator beta hat GLS reduces to the OLS estimator. If theta is equal to 0, you get 0 here, you get 0 here. So, you get this within estimator, and then you have this term 0, this term 0. So, you get within estimator here. Then you can easily verify the expression for w 1 for theta equal to 0 is w x x inverse w x x, which is identity matrix. So, finally, you can easily verify that you get the OLS estimator w x x inverse w x y, which is equal to x transpose q d x inverse x transpose q d y. Further, this GLS estimator involves some unknown parameters. So, it involves theta. To obtain the feasible GLS estimator, you replace this theta by its consistent estimator given here. So, if you replace theta by this constant estimator, you get the feasible generalized least squares estimator. So, in this lecture, we have considered the estimation of one-way error component model with fixed effects as well as random effects. In the fixed effects model, we need to have some kind of transformation, like we take first references or we take deviations from individual specific means, so that we get rid of the correlation between the explanatory variables and the random error component. In the random effects model, we have considered within estimator and between estimator. We have also discussed the generalized least square procedure for estimating the regression coefficients, and then we observe that the generalized least square estimator is a weighted average of within estimator and between estimator. In the next lecture, we will consider two-way error component model, then we discuss the estimation of two-way error component model. We will also discuss the prediction in panel data models. So, I am going to stop here. Thank you.
Hi, my name is Gillette Sam and I teach sociology at IIT Kanpur. One of the things you must have noticed if you read or if you talk to people around you is that they often refer to something called globalization, or they often say we live in a global world. What does this mean? Today I'll tell you about how to think about globalization or interpret the word global in a sociological manner. When sociologists refer to globalization, they refer to three things. The first is that that it involves transplanetary processes, which means that something is going on across multiple borders, right? The second is that it involves heightened liquidity and interconnected flows. Now, by liquidity, and this is a term that was coined by the sociologist Zygmunt Bauman, we refer to the increasing interconnectedness of things across the globe, but we also refer to increasing instability across the world, which means that potentially something that is occurring many kilometers away from you actually influences the place that you live in. So, if there is a natural disaster happening in one part of the world, maybe that causes people to migrate from that area and they come and settle where you stay. So, that is what we mean by liquidity. And of course, when we are talking about liquidity, we are talking about things that are really moving from one place to the other. Now, the third aspect, and this is something that you may not conventionally come across in the way people use globalization, is that of structures. So, let's take an example. Supposing I, as an Indian citizen, wish to visit a foreign country. Let's say I want to go to South Africa. can I just pick up my bags and hop on the next plane and go to South Africa? Any logical person is going to say, no, wait, you need to have documents such as your passport or visa. Now, this passport or this visa is a representation of the larger structure that governs how people move across borders. So, we have things like border control, national security agencies that consider what kind of people are going to move from one place to the other, correct? So, when we think about globalization, an average person typically tends to think about things moving or people moving from place to place. As sociologists, we also consider that there are structures that facilitate or direct this movement across multiple borders.